Welcome to Altair Engineering Training and Support. I am Apur Bapat. Welcome you all in SAE SUPRA SAE India 2016 pre-virtual online training session. So we'll start with the agenda. That is, we have a 6-day training session, online training session, on which today, on the day one, I'm going to cover theory of FEM and CAE, plus 1D meshing, geometry editing of the roll cage, with some static analysis on the 1D mesh roll cage, including front impact, side impact, rear impact, torsional bump and rollover analysis. Then on day two, I'm going to cover 2D geometry editing and meshing of the roll cage, static analysis on 2D meshed roll cage, including front impact, side impact, rear impact, torsional bump and rollover. On day three, I'm going to show you how to do dynamic crash analysis on the roll cage, including front, side and rear impact analysis. Then on day 4, I'm going to cover 3D geometry editing and meshing, which includes knuckle, hub and brake analysis. Then on day 5, we'll see how to do suspension analysis using MBD, motion solve and motion view. On day 6, we are going to see the computational fluid dynamics using AccuSolve and AccuConsole. So we'll start with the theory of FEA and CAE. So the first question is, why do we carry out meshing and what is FEM? So the basic idea of FEA is to make calculation at only limited finite number of points and then interpolate the results for entire domain, that is surface or volume. Any continuous object has infinite degrees of freedom and it's just not possible to solve the problem in this format. Finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing nodes and elements. So we have an infinite number of points if I consider this plate, and we cannot calculate all the stresses or deformation at these number of points. So we divide these number of points into some finite, and with the help of these points we create a shape which is called as element, and this complete process is called meshing. So FEM is a numerical method, mathematical representation of actual problem. It is an approximate method. So the finite element method only makes calculation at limited finite number of points and then interpolate the results for the entire domain. Finite, any continuous object has infinite degrees of freedom and it is not possible to solve the problem in this format. The finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing nodes and elements. Element, all the calculations are made at limited number of points known as nodes. The entity joining nodes and forming a specific shape such as quadrilateral or triangle is known as element. To get the value of variable, say displacement, anywhere in between the calculation points, an interpolation function as per the shape of the element is used. Method. There are three methods to solve any engineering problem. Finite element analysis belongs to numerical category. How the results are interpolated from a few calculation points. It is okay that FEA is making all the calculation at limited number of points, but the question is how it calculates value of unknown somewhere in between the calculation points. This is achieved by interpolation. Consider a 4-noded quadrilateral element as shown in the figure. A quad element uses the following linear interpolation formula. FEA calculates the value at outer nodes 1, 2, 3, 4, that is A0, A1, A2, A3 are known. The value of variable anywhere in between could be easily determined by just specifying x and y coordinates in the above equation. For 8-noded quadrilateral, the following parabolic interpolation function is used. What is degree of freedom? That is DOF. In the example, an object is fixed at one end and a force is applied at P. Due to the force, the object deforms at point P and gets shifted to new position P dash. When can we say that we know the solution of the above problem? If and only if we are able to define the deformation position of each and every particle completely. The minimum number of parameters, motion, coordinate, temperature, etc. required to define the position of any entity completely in space is known as degree of freedom. Consider the following 2D planar problem Suppose the origin is at the bottom left corner and is known. To define the position of point A completely with respect to the origin, we need two parameters, that is x1 and x2. In other words, two DOF, that is translation x and translation y. Consider that point A is a part of line. Now, one angle should also be defined in addition to two translation, that is 3 degrees of freedom, that is two translation and one rotation. Suppose point A and B are shifted out of plane and the line is rotated arbitrary with respect to all the three axes. The minimum parameters to define the position of point A completely would be 6, 3 translation and 3 rotation. DOF is very important concept. In FEA we use it for individual calculation points. The total DOFs for any mesh model is equal to the number of nodes multiplied by the number of degrees of freedom per node. All the elements do not always have 6 degrees of freedom per node. The number of degrees of freedom depends on the type of element, 1D, 2D, 3D, the family of element, thin shell, plane stress, plane strain, membrane, etc., and the type of analysis. For example, for a structural analysis, a thin shell element has 6 degrees of freedom, displacement unknown, 3 translation and 3 rotation, while the same element when used for thermal analysis has single DOF per node, that is temperature unknown. For a new user it is a bit confusion, but it is lot of logical engineering and mathematical thinking behind assigning the specific number of degrees of freedom to define element types and family. So now we'll see different types of elements. 1D, where one of the dimension is very large as compared to the other two. Element shape is line. Additional data from the user is remaining two dimension, that is the area of cross section. Element types are rod, bar, beam, pipe, axisymmetric shell, etc. Its practical application is long shaft, beam, thin joints, connection elements, etc. 2D, two of the dimensions are very large in compared to the third one. Element shape is quad or tria. Additional data from the user is remaining dimension, that is thickness. Element type is thin shell, plate, membrane, plane stress, plane strain, axisymmetric solid, etc. Practical application is sheet metal part, plastic component like an instrument panel, etc. 3D, all dimensions are comparable. Element shape is tetra, penta, hexa, pyramid. Additional data from the user is none. Element type is solid. Practical application is transmission casing, engine block, crankshaft, etc. Other type of elements are mass, point element, concentrated mass at the center of gravity of the component, spring, translational and rotational stiffness, damper, damping coefficient, gap, gap distance, stiffness, friction, rigids, RBE2, RBE3, and welds. So now we will see 1D meshing. So first is when to use 1D meshing. One of the dimension is very large and compared to other two, then we use 1D meshing. Element shape is line. Additional data from the user is the remaining two dimensions, that is the cross sectional area. Element type is rod, bar, beam, pipe, axisymmetric shells, etc. Practical application is long shaft, beam, pin joints, connection elements. So types of 1D element is rod. It is used for tension compression and torque for the same software, for some softwares. So that is tension compression members, trusses, shaft subjected to torque, connection elements. Bar elements have all 6 degrees of freedom, applicable for symmetric cross section, shaft subjected to multi-axial loading, bolted, welded joints, connection elements. Same as bar, but also support unsymmetric cross section, that is shear, center and warpage. Same as bar for unsymmetric cross section. Pipe, same as beam except it has internal non-zero diameter. Piping system, structural analysis. Axisymmetric shells, UX, UZ, RY. Z axis of the symmetry, X as radial axis for objects symmetric about the axis of rotation and subjected to axisymmetric boundary condition. Thin shell pressure vessels, cylindrical, conical objects, etc. 2D meshing. When to use 2D elements? 2D elements are used when two of the dimensions are very large in compared to the third dimension. Element shape is quad and tria. Additional data from the user is remaining dimension, that is the thickness. Element type is thin shell, plate, membrane, plane stress, plane strain, axisymmetric solids, etc. Practical application is sheet metal parts, plastic components like instrument panel, etc. Why is 2D elements is carried out on a mid surface? Quite often, the geometry of thin-walled 3D structure as shown in the image below is simplified to a geometric model with low dimensionality. This is typically called a mid-surface model. The mid-surface model is then meshed with 2D element. Thus, there is no need for detailed volume mesh as the thickness of the geometry is virtually assigned to the 2D elements. Mathematically, the element thickness specified by the user is assigned with half in the z plus direction element top and the other half in negative z direction element bottom. 2D elements shapes tria. We have a first order tria with 3 nodes, second order tria with 6 nodes, then a chord element first order that is linear chord and 8 noded chord element that is parabolic chord. Then 3D elements, when to use 3D elements? So 3D element should be used when all the 3 dimensions are comparable. Element shape is tetra, penta, hexa and pyramid. Additional data from the user is nothing. Element type is solid. Practical application is gearbox, engine block, crankshaft, etc. 3D elements are tetra, linear tetra with 4 nodes, parabolic tetra with 10 nodes, penta, linear penta with 6 nodes, parabolic penta that is second order penta with 15 nodes, hexa or brick element with 8 node linear hexa, 20 node parabolic hexa or brick, pyramid elements, 5 noded pyramid element or 13 noded pyramid elements. So we'll start with 1D meshing and geometry editing of the SUPRA roll cage. So first open the software as Altair Hypermesh. You will see a user profile window once you start Altair Hypermesh. So select the user profile as OptiStruct as we are trying to perform the static analysis. So for static analysis, we select the solver as OptiStruct. So select the user profile as OptiStruct. Click OK. It will load the required templates. Then open the file. So I have a roll cage structure here. I request everyone not to copy this roll cage because this roll cage is not at all safe and not designed as per the rule book. Intentionally I did that because sometimes people just copy the roll cage whatever I am showing here. So it is I am using this roll cage to show you how you can do the same process on your roll cage. So please don't try to copy this roll cage and have a similar type of roll cage because this roll cage is not at all safe. So this is my roll cage data. So once I'll get a roll cage data, I'll start with the process. So my first step is to create the material. So to create the material, I will click on material collector icon. At the bottom of the screen where my mouse pointer is, you will find a material collector icon. I am highlighting it here. This is a material collector icon. Enter the material name as steel. Define a color. Enter the type as isotropic because I am using isotropic material. Card image as matte 1. Click on create edit. Enter the value of E, new and row. Click return. Again click return. Then I will define the cross section, the next step. So to define the cross section, I will go to 1D page. On 1D page, I will click on hyper beam. So I will select the standard section radio button. Select the standard section library as hyperbeam and standard section type as thin walled tube, as I am planning to have all my cross sections as circular cross section. So standard section library is hyperbeam and thin walled tube. If you have a square section, you can use a thin walled box. So click create. I will enter the outer radius as say 12.7. So that means my outer dia is 25.4 and the inner radius is 11.7. So I have a thickness of 1 mm. Once I have done with this, so you can see at the right hand side of the screen, it has calculated everything like area, moment of inertia, centroidal, then polar moment of inertia, radius of gyration, everything it has calculated as per the dimensions I have given. So again I will move back to hypermesh screen. So to move back to hypermesh screen, click on this highlighted icon. So you will get back to the hypermesh screen. On the model browser you can see a beam section is being created, a material has been created. So now I will define a property. So to define a property, I will click on property collector icon. Enter the property name as roll cage pipes. Define a separate color to it. Select the type as 1D, card image as P-beam, material as steel, and define the beam section which we have created earlier. Click on create edit. It has automatically taken the area IXX, IYY and J required to define the cross section. So I will click return. Again click return. So I have defined the material cross section property. Now I will update this on the component. So I will click on component collector icon. Enter the component name. I have already a component, so I will make that as update. So I will go to update this component and select the property which I have created earlier and just click on update. So I have updated this component. Now I will go for meshing, but before going to do the meshing, I will first check whether all my line data is properly connected or not, because if it's not connected, then my meshing will also not get connected. So I'll go to line edit and I will check one by one whether my geometry is connected or not. So I will just click. It should be start or end line has to be properly connected. If it's not, then I will connect it. I will show you how you can connect these line datas. So you can see the start and end line of all these pipes are proper. So here you can see this is not proper. So it has a straight line, but there is a connection here. So I will use this line to split it. So this is now proper. Similarly here also you can see this is a straight line. So I will use this line to split it. Similarly here also I will use the line to split this. So I will just click on these lines and see whether the start and end line is proper or not. If it's not, then I will do it. So here you can see this is a single line, but it has to be split from here. So what I will do now, I will use this cut line to split this. Similarly here also I will use this split line. So here also it is not proper, so I will use this split line to cut. Here also I will use this split line to cut. So now this is proper, this is proper. So I have to check all the lines and they have to properly connected. Otherwise my meshing will not get connected. So here these two lines are not properly connected, so I will split this lines again and this line also. So now my geometry is properly connected. I have just checked now. So I'll move to the next step, that is meshing. So I'll go to 1D page. To do 1D meshing, I'll go to 1D mesh, 1D page, line mesh panel. Click on line mesh, select lines all, select the element configuration to bar 2, select the property which I have created earlier, enter the element size, whatever element size I want. So let's assume I want element size say 15 or 5, whatever I want, and click on mesh, click return. So now if I turn off this geometry, this icon is used to turn off and on the geometry. If I highlight it, you can see this icon is used for turning off and on the meshing. So this is for geometry and this is for meshing. So if I off this, and this is for meshing. So as I have already told you, this my icon is, if I go to mask element and mask one of the element, so this is my 1D element. If I press shift F2 and add the nodes, so you can see this is the start end and end of my element. I can see in a 3D also. So this is how my element will look like. So as you can see, there are some elements which are not completely in 3D. So if I mask this element, you can see this is how my 3D element will look like. So this is my 1D and this will be my 3D. So as there are few elements which you can see are not there itself. You can see if I take these elements in 3D, so you are not able to see the elements. So this is because the orientation is not proper. So if my element length is in z-axis, then the cross section has to be in xy plane. If it's in zx plane or zy plane, then I cannot see a 3D element. So I have to update it manually. So to update it, I will go to 1D page. To update this meshing which is not proper, 1D page, bars panel, select update, just manually select these lines. So I am just referring that what are the elements which are not properly connected, or not properly not connected, it's properly not oriented, and then I will make it in a line mode. So I know these are the elements which are not properly oriented. So I will off this geometry, and select these elements. If I don't update them properly, then it will create an issue with the meshing. So I have to update it with proper elements. So select all these elements which comes on this line. and you have to just update its orientation. That's it. As I have done line meshing, that's why this orientation error is coming. If you have done the manual meshing, then the orientation error will not come. But that is more time taking process. So updating these elements is any day better. So just select all these elements because they are all in the same axis. So I will, once I complete the selection process, I will just update all these elements. So as you can see, I have selected all the elements which are not properly oriented. So I will change the orientation to y-axis, define a property, element type as C-beam, and just say update, and update all of them. And again I will check the 3D representation. So you can see now I am able to see all the elements in 3D. So this is done. My meshing is done now. Now the next step is to create the load collector. So to create the load collector, I'll click on load collector icon, which is here. I will create all the load cases, that is the 6 which I have already shown you, that is front, side, rear, rollover, torque, torsional, bump, all in the first one shot, and solve it and see the results in one shot. So I will create the load collectors as front impact force, create, side impact force, create, rear impact force, create. I can just say plus, so I can see that is what are the things I have created. TOR, torsional force, create, bump force, create, rollover force create, and normal modes give a card image as EIGRL, create edit. V1 is the initial velocity, V1 is the maximum velocity, and ND is the number of modes. Then front impact SPC, define a separate color to it, create. Side impact SPC, create. Rear impact SPC, that is single point constraint, create. Then torsional SPC, click create. Then bump SPC, create. Then rollover SPC, create. Then normal modes SPC, create. So I have created 7 forces, 7 SPC, that is 7 reaction force and 7 action forces. So I will keep applying them. So I will make front impact as the current. Go to analysis. To apply the force on model, I will go to analysis page, forces panel. Select the nodes on which I want to apply the forces. Nodes, save. So I can see how many nodes are there at the bottom right corner of my screen. Here you can see there are 21 nodes on which I want to apply the force. So let's assume I want to apply a force of 10,000 Newton divided by 21. So I will enter the value of magnitude as minus this value because the direction of force in minus x axis. So I will select here the axis as x and click on create. So it has created the force, so I can increase the magnitude percentage. So I can see the representation of forces as the arrow here. Now similarly I will parallelly create a front impact SPC, that is the reaction force. So analysis, to create an SPC I will go to analysis page. On analysis page I will click on constraints panel. So I will click on constraint panel, select the suspension mounting points, front suspension mounting points, and constrain it to 3 degrees of freedom. I can increase the size of the constraints. Similarly, rear suspension mounting points and constraints all 6 degrees of freedom. So I will off these two. Now I will make side impact as the current. Go to analysis forces. Select the side impact member nodes, all the nodes which comes under the side impact member. Click nodes, save. So at the bottom I will have the total number of nodes I have selected. So these are 52. Again, let's assume 10,000 divided by 52. So this time the direction is z-axis positive, so I will enter the positive value as z-axis and say create. So you can see a force has been applied here, and similar constraint I will apply. So I will make the SPC as current, analysis constraint. Again the suspension mounting points I will constraint. these are rear, these are front and rear. So I will opt these two and make the current as rear impact, analysis, forces, select the rear one, rear suspension, rear member to do the rear force analysis, nodes, save. So I have 34 nodes. So 10,000 divided by 34 is this number. I will copy this. Now the direction you can see here is x-axis positive. So I will say create and apply the constraint. So I will make rear as the current, turn off this and apply a constraint here on the suspension mounting points and front suspension mounting points. To all the 6 degrees of freedom, create. I will turn off these two, make the torsional as current, torsional force. So torsional force I will apply on the suspension mounting points. So front suspension mounting points, same force, let's assume 2500 in y-axis, create. Similarly, the other suspension mounting points as 1, 2, 3, 4 in negative direction to simulate the torsional. So this I have done. So I will lower down the size value and constrain the rear end. So I'll make the rear torsional SPC as current and constrain the rear suspension mounting points. So you have to constrain where you are planning to have the suspension mountings. So I will turn off this. Then I will make bump as the current. So analysis, forces, apply a bump force at the suspension mounting points in the front. You can do a rear bump also of 1250 if I want 7,000 10,000 and make SPC as current. So analysis, constraints, constraint the rear end suspension mounting points to all 6 degrees of freedom. Then turn off these two and I will before going to rollover, I will first apply the modal SPCs. So I'll go to constraint. So I will constrain all front and rear suspension mounting points for normal modal analysis. Similarly, rollover SPC also, I will constrain all of these. Now I will make the rollover as current. So for rollover analysis, my forces will be on the rear and front roll hook. Let's assume at 45-degree downward, this direction. So if I go to forces panel, I don't have a directional degrees of freedom. So what I will do is I will create another system, a local coordinate system here. So I'll go to tools. So analysis page system. Select a origin node on which I want to create a system. So origin, x-axis, xy plane, and say create. So you can see here I have created a system. Now the next step is I'll go to tools, rotate, and select systems here. Select this system and rotate it to 45 degree. So now I have this x-axis in 45 degrees. You can see here. So now instead of using global XYZ, I will use this local system XYZ to apply the forces. So I'll go to analysis, forces, select the nodes of front row loop and rear row loop. Instead of this global system, I will change it to local system and select this one. Select the x-axis. So here it's positive x-axis in this direction. So I will enter the value as negative. So first I have to calculate how many nodes I have. So I have 83 nodes. So 10,000 divided by 83. So I am going to apply a minus this force, say create. If I increase this, so you can see I have applied a directional force on this, angular force. So to create an angular force, you can do like this. I am assuming my rollover is something like this. So if you have a rear one, you can apply from this direction. So it depends on your case, but I am showing you how you can apply angular forces. So this is done now. So I will define the type of analysis based on the load collectors. So to define it, I'll go to analysis page. On analysis page, I will click on load step. Enter the load step name as front impact. Select the type as linear static, SPC and load. So I will select SPC as SPC, load as front impact force and say create. Similarly, side impact, SPC will be SPC. For side impact, load will be side impact force, create. Rear impact, SPC will be rear SPC and rear impact force, create. Then torsional, SPC will be torsional SPC, load will be torsional force, create. Then bump, SPC will be bump SPC, load will be bump force, create. Then rollover, SPC rollover, load rollover, create. Then change the type as normal modes, enter here normal modes. So SPC as normal mode SPC and check the box in front of method structure and give here normal modes, say create. So I have 7 load cases. Now I will save this file and solve this using OptiStruct. So to solve this using OptiStruct, I'll go to analysis page, OptiStruct. Select the export option to all, run option to analysis, memory option as default, and click on OptiStruct to start the solver window. So my analysis has been completed. So I'll click on results to open a hyperview to view the results. So now we will see the results of displacement. So I will click on contour. So this is the displacement value because of front impact. So the maximum displacement is coming at this point. Then side impact displacement, rear impact, torsional, bump, rollover. Then stresses, C bar, C beam axial stresses, averaging method to simple and say apply. So these are the stresses due to front impact, side impact, rear, torsional, bump, rollover. If I want to see the animation, I can click on this play button. If you are not able to see the animation, go to deformed icon and increase the scale value. So this is the animation. Because of front impact, then side impact, rear impact, torsional, bump, rollover. Also you can see the animations because of modal. So first mode, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. So these are the different modes, means results of modal analysis for different mode shapes. So in this way, I have ended with this today's day 1 session. Thank you very much for attending this webinar. If you have any queries, feel free to contact us via edu-support@india.altia.com.